Ladies and gentlemen of Blue Hat 2025, trust nothing.
Hi everyone, welcome to my talk. Thank you for being here. In today's talk, I'm going to showcase the talk Unlocking the Past, Securing the Future. So, so the clicker doesn't work, but now it works. Great. Okay, so my name is Tomer Goldschmidt. I'm a vulnerability researcher at Clarity Team 82. And in my day job, I find vulnerabilities in devices that are used in critical infrastructure. And we report them and disclose them in a way that allows the industry to be more secure and more safer. And also, we present our talks and our blogs in order to make the industry more knowledgeable. As you can see, we do a lot of research in devices such as the device you can see in the image in the slides. All sorts of devices ranging from IoT to industrial controls systems and also medical appliances. So I want to tell you a story about the first assignment I got when I got to Clarity Team 82. So the first assignment I got was to find a vulnerability in a device called the Seymour HMI. Now, maybe some of you know, but I guess most of you don't know what is an HMI or what is Seymour. So I asked myself the same question, what is an HMI? Well, the first question was, what is an HMI device? And so an HMI device is actually an industrial panel that is used in industrial facilities in order to facilitate monitoring and controlling of industrial processes. Now, this includes being able to monitor the process that is actually going inside our factory. So you've got an engineer that wants to verify that an industrial boiler is working fine and it works just at the right temperature. Then that engineer could just go to the HMI panel that is beside it and could view what's the metrics of this appliance working right now. Now, the HMI is actually is usable using a graphic interface, and is actually very nice, and an engineer can actually change it a lot to facilitate what their needs. So yeah, as you can see, this is an image that demonstrates how it will look in a facility, in a factory floor, where an engineer might walk. And as you can see, there are a few boilers and the HMI panel that instructs what the metrics of those boilers ongoing in real time. So the second question I got to ask in my first assignment was, what is the Seymour HMI device? So the Seymour device is actually manufactured by Automation Direct, and it's an HMI panel that is often used in industrial facilities, for example, water treatment facilities. And it's actually a device that is based on Windows operating system, Windows CE specifically. Now, I also asked myself, what is a Windows CE system? Because I never stumbled with this operating system in a research environment. So the Windows CE operating system is its initial release is quite old, since 1996. It's an operating system that is used in legacy environments. It's used in all kinds of scenarios and settings. It supports all kinds of architectures, and it has various versions along the years that it's been developed. Yeah, so that's what I got to know at the first glance of this device. Now, when we are talking about Windows CE systems, we can see them all around us without even noticing it. I guess someone here might have saw in the train station or at a bus station where there is the ticketing system. Then you might notice that sometimes these applications crash and you see the blue screen of death, or the screen of the actual operating system not in a kiosk mode. So yeah, it's all around us and we don't even notice it. Now, the Seymour HMI specifically supports two main features that are very pleasant and nice for engineers and for the industry as a whole, which are the ability to access the device from the network interface. Now, as you can see, there is a web interface and also an FTP server that runs on the device that allows engineers to remotely access their HMI from a remote location. Now, this is really interesting. And when I figured out that it has these capabilities, I wondered how many devices are actually exposed online with these services actually exposed themselves. And what you know, they do have a lot of instances of these devices exposed online, and specifically 3,000. And this is only when you're looking through a simple query using Shodan. And as you can see, they expose a lot of metrics about industrial facilities all around the world, from meters that tell you the metric of temperature to centrifuges that spin around, and a lot of different components that are used in critical processes all around us. And so when I first understood all of this setup, it became very clear for me that the scenario I want to research and to find vulnerabilities in my research with regard to the scenario was that an attacker would be able to infiltrate into a facility network using an exposed HMI that is accessible in the online. So in our case, the attacker would just try to attack and exploit a vulnerability in the services exposed online and would be able to run code on the HMI, and by doing so, infiltrate the network of the industrial facility. Yeah, so this is our goal, finding an RCE on an exposed HMI service. And when we are talking about finding vulnerabilities in embedded systems and devices that are exposing services, the first thing and the first step we usually do is to gain access to the firmware of the device. We want to understand how we can extract the file system from the device, and it's usually from the firmware that is embedded into the device. In that case, the CMOR HMI was quite easy. We just went to the site of the vendor, and we managed to download the software used to program this HMI. And from that software, we managed to gain access to the firmware itself. Now, when we got to the firmware itself, we wanted to extract the actual file system. We wanted to get hold on the applications that run on the device and the logic that operates it on a daily job. And so the first thing I did was to open an X editor and to review what's the contents of that file. And reviewing that file, I noticed that it uses a proprietary archiving format that was very easy to understand. And so using a simple binary analysis, I managed to extract the contents of the file system from the firmware. Here you can see the actual construct that I used in a Python script to extract the contents of the format of the firmware. For instance, you can see the file name and the sizes, all sorts of flags. And we used that because we needed to extract the applications and the DLLs, the libraries, the contents, and the logic of the device itself. And as you can see, we did manage to extract a lot of files, and actually we also had a path into the firmware itself. And yeah, so we got hold on DLLs and XZs, and also assets used by the device. So in our scenario, we wanted to attack the FTP server. Now, in our case, it was the WSFTP exe that was extracted earlier. And just one note about FTP, a textual protocol that is used in a lot of places, where a client sends commands to the server and is able to interact with the server in order to transfer files from one location to another. Here, for example, you can see the current directory you are at in the server. And so the first thing I did was to open Ghidra and to try and look at the strings that are used in that binary in order to get understanding to where could the logic be in that binary that handles the actual request from the client. So in our case, we can see a lot of commands that are used generally in FTP. And we managed to find a routine that actually handles the FTP commands, and we tried to understand what could be wrong or what could be vulnerable in these routines. And so when looking in the routine that handles the FTP commands from the client, we noted that some of the commands require authentication, which means that a client needs to authenticate to the server in order to run this command, which means that we, as attackers that don't have the credentials, can't actually use this command and can't actually exploit a vulnerability in that command in a more direct way. But we did notice that some of the commands don't require authentication, as it's usually. In this case, it was the type command. Now, the type command is specifically for the transfer of different contents of files. It depends on the type, and using this type that you can set using the client, you can determine what file are you going to send to the server so it could digest it more easily and more effectively. And so we wanted to target the type command in order to gain a pre-authenticated attack surface and to actually use this pre-authenticated attack surface to exploit an RC. Now, here you can see the explanation for the type command, and we got to this function, the type command function, that is handling the routines that actually effectively handle the type that is supplied by a client. Now, here you can see that the first parameter is a white-char variable, and in our case, it was the actual attacker input that is provided through the interface, through the network connection. And we noticed that the attacker input is actually used in some white-char's copy. Now, just to make a rundown on white-chars, when we are talking about white-chars, we're talking about an encoding that is used widely in Windows operating systems, in which a representation for a character is with 2 bytes encoding. Now, in the case of, for example, 41 hex, that is a representation for an ASCII A, capital A, we are transformed into a 2-byte representation with a null byte and the 41 value. So we continued with the wchars copy routine in the function earlier, and we tried to understand if there is any kind of vulnerability. Because it's a procedure to copy contents from one buffer to another, we were intrigued if we could find some kind of a buffer overflow in this routine. And as you can see, we did manage to find that source variable is actually the attacker-controlled input, and the destination is the variable that's going to contain a pointer to the destination buffer. And using this fairly mundane or naive construct of code, we managed to understand that they have actually an insecure memory copy. Now, this is because the actual attack content is determining the actual length of the copy, which means that an attacker could supply a buffer that overruns a buffer that is limited to some kind of length. And when we saw this, we noted to ourselves that the white-char's copy is actually vulnerable. We have an insecure, an unsafe memory copy, and we did note also that the copy is done into a buffer that is limited to 10 bytes on the stack. Now, this was a great win, because when we understood that, we actually understood that we have a relevant primitive that we could use in our exploit. Now, this was all right. We have the vulnerability, the classic stack buffer overflow, and we can just go on with our exploit. We wanted to develop it, and I was thinking that it will be quite easy, but I needed a debugger or something to use in order to operate on the device. But I came to the first hurdle, which was that my device was actually in a kiosk mode. This meant that I can't actually interact with the device and really connect with the debugger to my physical device to actually interact with the server and to note what is actually happening in the server. Now, this is important because I wanted to understand where am I overwriting the buffer, what kind of addresses do I jump to when I do my exploit. And this meant that I can't actually use my physical device. But then again, I did have a solution in my head, which was that I can use an emulator. Now, I figured to myself that Windows CE is so old, and as a legacy system, I wondered if there is any kind of system that is simulated or emulated. And I did manage to find a specific Windows CE 6.0 emulator that I did manage to set up and make work. And so I placed my emulator with the WSFTP-exe, and I just tried bluntly to exploit this vulnerability and try to see what happens, without even knowing what could actually happen, just to validate there is a vulnerability, there is an issue here. And as you can see, I did manage to crash the WSFTP-exe process when I supplied the actual attacker input. Now, that's OK, that's great. I validated that I have the vulnerability accessible and could be exploitable in some way. But I needed to debug this process. And so the search for a debugger was quite cumbersome, I would say. But I did manage to find that Visual Studio 2005 supplies a specific debugger for applications for Windows CE. Now, that was great. It would allow me to actually debug the process, but it wouldn't work on my host machine that is newer Windows system. So no problem, just raise a Windows XP system that matches the dates and the versioning of the Visual Studio. And yeah, I had my setup ready. Now, this is my hefty setup. I had my host machine running a VM, and in that host machine that is Windows-based, the VM actually ran the Windows XP, which ran the actual Visual Studio and Windows CE emulator. Now, that's a lot of Windows, I know. Yeah, so this was my setup, and it wasn't great, but it did allow me to continue my research. And this was the most important goal. I needed to continue my research, and so I did what I did. Now, when I connected my debugger to the actual device emulated in my system, I did manage to gain access to the process listings, and I figured, OK, now it's smooth sailing. I'm going to just be able to debug my process, and everything is going to be just great. But I was stumbled with some error message, a specific message that entailed some kind of an issue with using a Visual Studio. Now, the thing is, Visual Studio is actually a development utility, which means that it's not built for actually debugging processes or applications that aren't developed by the actual researcher. So for instance, here we are trying to connect to the process and to interact with it, to actually debug it, but we don't have the actual source code. And that's OK, because when you are researching, most often you're not going to have access to the source code of your application, of your target application. And this became apparent that it's not possible to use Visual Studio Debugger to debug and research actual applications where you don't have the source code. And so this led me to a wormhole, or some kind of an adventure, I would say, that was very interesting for me, because I wondered, how does Visual Studio actually work? How does Visual Studio does all the debugging? Now, I don't have an actual debugger, and I need to complete my research. So I decided, OK, I can just go on and research how Visual Studio does its thing, how it debugs processes, and I could use it to build my own debugger. And I believe that it's possible in a quite recent time, and I went on with that. So I wondered, how does Visual Studio actually works in regards to debugging? And what I came to the understanding was that Visual Studio has several components that are specifically agnostic to the architecture of the device that you're intending to debug. Here you can see actually the different folders that contain the components needed for debugging. And as you can see, there are many architectures. There are MIPS, ARM, there are actually more, x86, and also PowerPC. So many types of components that could be used in all sorts of systems. Now, when I started my, I would say, adventure into this part of the research, I was, I would say, hurdled or stumbled with a blocking feature that was that they were missing a lot of documentation. No documentation was actually relevant or really helped me using this utility. But I just went on with my research. I just branched off to the debugging part of things. And I did manage to analyze the common client executable and the EDBG-TL DLL, where I did manage to understand that they are implementing an interface to actually interact with the device and to facilitate debugging, and the second one to allow an API for the debugging itself. So with that understanding, together with my knowledge, I went on with my research and tried to understand what is the actual interaction between the debugger to the actual endpoint that we are debugging. And so I did have from the configuration phase of the debugger a hint, which was the actual port used to interact with the emulation of the device. So opening Wireshark, I did manage to analyze this interaction between the debugging utility and the debuggee, the emulator. But I was stumbled with the fact that their actual protocol doesn't implement any debugging facilities. It's actually used for sending and executing and actually controlling the device from remote. So it would enable me to edit registry values. It would enable me to send files. But it wouldn't allow me to debug a process, really. So I asked myself, where is the actual debugging protocol? And soon enough, I managed to find that there is a second port that is used, specifically the 6510, that was actually very interesting. So I opened Wireshark again, and I looked into the packets, and I noticed something that was quite intriguing, which was that there were strings that were related to debugging. Now, this, I would say, would be a smoking gun where I am in the right direction. I think I got to the point where I see the protocol used for debugging. So a few hours later, I am done with my analysis of the network traffic, and I have a format for the packet used for a specific endpoint. Specifically, I managed to, here I'm showcasing one packet, such as the process memory read, where I just managed to analyze and understand that this is the actual debugging protocol that is used to invoke methods in Windows API, Windows debugging API. And I noticed that it's actually quite easy to implement. So I decided to follow some correlation between the actual endpoint in the protocol to the actual read process memory APIs in Windows. And using this understanding of and correlation, I could just facilitate my own interface using the debugger. And so I implemented a simple protocol manager in Python, and then I created a simple API to debug any process you want on Windows CE. And this was quite cool. I could script my own way into debugging processes, into hooking to different types of functions. And awesome, I've got simple API to use. And yeah, so what I got from this branching of the research was that I had a good understanding of how Visual Studio works in this proprietary scheme. And it actually allowed me this knowledge to create a basic client that allows for scripting and debugging. Now, the thing to note here is that scripting and using scripting language as a debugger is not, it's very clunky, I would say. And so I decided I might just go a little bit further. And I wanted something that was easy to use, that I can use in my research For example, I thought to myself, this wouldn't be the last application I might stumble in a Windows CE operating system. And I would just need to handle this occasion again and again, building a scripting to debug these applications. So I decided to go further and built a textual UI that I could use in order to debug actual applications in Windows CE. So the specific UI I used and all of this wraparound over the API was actually very nice. It allowed me to debug in a reasonable way and in a possible way, I would say. And yeah, so let me show you a little bit about the debugger, and then we'll continue on. So I used Capstone for the disassembly of code that is used in the actual executable. As you can see, it's ARM assembly. And I used Textual, that is a Python library that is used for the actual textual UI. And I managed to assemble all kinds of features along the way. So for example, I built a hex editor that could allow me to patch memory live on the application that is running on an emulator. And this was great because I needed to actually create an exploit later. I also created a thread context that allowed me to review and to edit registers in a reactive way, which was also great because I needed to specifically determine all kinds of branches, and this allowed me to do that. And so I was also able to place breakpoints and to use this debugging utility. And I did manage to finally exploit my vulnerabilities and to create an exploit chain. So now is the part of the presentation where we are going to use my utility in order to actually debug and find an exploit chain for the vulnerability we found. So if you remember, we have the white chars copy that is copying from the attacker input into a stack buffer. And the stack buffer is limited to 10 bytes, so the actual buffer overrun and the overflow would be very, very significant. So the first thing I did with my debugger was to place a breakpoint on the return address from the function, and then to fire away my attacker exploit script, or snippet, I would say, sending multiple A's in ASCII. And so when I got to the return address, I did note that I had pretty much, I have full control over PC, or at least that's what I thought, with values that I sent. As you can see in the hex view that is presenting the stack pointer, it represents the actual contents of the stack. We can see that we're going to be popping into the PC register, returning from the function frame, and having the content that I sent in white chars encoding. So that's awesome. I have control over PC and also on 2 other registers. But values are actually white chars encoded. And that's a problem because that means that I can't really use these values to target specific addresses that I want. And it's not arbitrarily controllable by me. But in the end, we don't actually we specifically have the ASCII range that is encoded into null bytes and the byte value of the character. But we actually can encode different characters in different languages or emotes, emojis. And so what I did was to create a table that enumerates all over the range of the encoding used in white chars encoding. And I did manage to find a lot of values that were usable for my exploit chain. Now, for example, here you can see that I highlight the 89, where you can see that we have 2 bytes 20, 30. Now, that made my exploitation chain very clear. What I wanted to do was to find characters that encode to valid addresses, and then to construct a ROP chain that will call system in the end, that would allow me to actually exploit the system and run code and commands on that operating system. And so one of those gadgets that I used was, for example, the 89, that using 8901 as the character encoding or the raw contents I'm going to send as an attacker, it would actually be translated into that address that was usable in my attack chain. And so I reconstructed my snippet just to test to see that I can actually target that address. And before I continue on with my ROP chain construction, and I did manage to overwrite that address with the actual address I targeted. Now, in that case, this is little endian form of the 01-2030 address. So in basic terms, what I had was I could actually overwrite the address that I'm going to jump to with any address that is viable through my encoding translation table. So what's now left was to actually take that table and use it as a filter to the addresses that are relevant for my ROP chain. Yeah, so in terms of finding that vulnerability and being able to exploit this bug, I did manage to finally exploit it using those addresses and construct a ROP chain. But in our case, this wasn't the actual essential, I would say, it wasn't actually the first thing that I did when I went on with this project. And so I had the addresses, and I had the ROP chain, and I pawned that system. And I managed to exploit and run code on that system, which meant that as an attacker, you could actually exploit it and run code on exposed HMIs. So we disclosed this vulnerability, and we actually got it to be fixed in the HMIs. So the industry was more secure after our research. But not only that, we did decide to make our tool open source to actually help the industry and to actually make it more accessible. Because in the end, these systems are critical and are used almost everywhere. Those are legacy systems, which means that they are code that is quite old, that was maintained before long ago. And with the hurdles I had in my research, we deduced that not a lot of researchers had their footprint into that area of code. And this meant that a lot of systems were potentially exploitable, having vulnerabilities that weren't on the surface because of that friction between you as a researcher to the system that you are trying to target. And so, yeah, we decided to make this tool available. And I hope that some people here in the audience or around the world maybe could use it to find vulnerabilities and to share their knowledge and research. And yeah, that's all from me. Thank you. Thank you very much.